Alright guys, and welcome back to my channel. Now in this video, we'll go ahead and be focusing on the topic of differentiation. And in specific, we'll want to go ahead and find the derivative of a function using the definition of a derivative. Now, I was planning on doing 2 examples on this video, but it would be rather long if I did that. So I'll go ahead and break this video up into part 1, where we find the derivative of f of x to be x squared. And in the second video, part 2, we'll go ahead and find the derivative of f of x to be the square root of x. So let's go ahead and jump right in and get started. Now, in order to go ahead and find the derivative of f of x, we'll have to rely on the definition of a derivative. Now, remember that in your calculus class, the definition of a derivative was equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. Now, there are 2 components that we're going to have to find to go ahead and appropriately find this limit. The first component that we're going to have to find is f of x plus delta x and f of x. Now, from the problem, we already know what f of x is. It's just x squared. So the only component that we really have to find is f of x plus delta x. And so let's go ahead and write that right here. F of x plus delta x. And to find f of x plus delta x, it's pretty simple. All you do is reference the original equation, and wherever you see an x, you just go ahead and plug in x plus delta x. And so following that rule, we get that f of x plus delta x is x plus delta x squared. Now when it comes to evaluating limit expressions, it's always a good idea to expand anything that requires expansion, such as this expression. And so we'll go ahead and expand x plus delta x squared. Now from algebra, you know that x plus delta x squared is just x plus delta x times another x plus delta x. And so we'll go ahead and use FOIL to go ahead and simplify this expression right here. And so we'll go ahead and multiply x times x, and then we'll go ahead and multiply x times delta x, and then we'll go ahead and multiply delta x times x, and then we'll go ahead and finish off with delta x times delta x. So starting off with the blue, x times x is just x squared. And then for the orange part, x times delta x is x delta x. And then for the second orange part, delta x times x is the same thing as the expression above, and so we have x delta x. And for the last part, delta x times delta x, we get delta x squared. And so now that we have all these components from multiplying x plus delta x times x plus delta x, we can go ahead and write x plus delta x times x plus delta x is equal to x squared plus x delta x plus x delta x plus delta x squared. And so by combining like terms, we get x squared plus 2x delta x plus delta x squared. And so we get that the expansion of x plus delta x squared is just x squared plus 2x delta x plus delta x squared. And so now that we have this expansion, and knowing that this expansion belongs to f of x plus delta x, we can finally start to find the derivative of this function by using the definition. And so recall that the definition of a derivative of f of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x, all divided by delta x. And so let's go ahead and plug in what we know. So we'll have the derivative of f of x is equal to the limit as delta x approaches 0 of f of x plus delta x, and that was just x squared plus 2x delta x plus delta x squared, and then minus f of x, but we know f of x is just x squared, all over delta x. Now remember, when it comes to evaluating limits, it's really important that we simplify the expression as much as we can to avoid an indeterminate form. And if we plug in 0 for delta x, we'll end up with a 0 in the denominator, which leads to an indeterminate form. And so we'll have to go ahead and simplify as much as we can before actually taking the limit of this expression, which is going to lead us into the derivative of f of x. And so let's go ahead and continue simplifying through algebra, and we get that the derivative of f of x is equal to the limit as delta x approaches 0. And from the previous equation, recall that you have an x squared right here and a negative x squared right there. And so when you combine an x squared with a negative x squared, those two just cancel out, and all you're left with in the numerator is 2x delta x plus delta x squared, all divided by delta x. Now, we're almost to that point where we're going to be able to evaluate the limit of this expression. All we have to do is somehow algebraically manipulate this expression to go ahead and make sure that whenever we do plug in delta x to be 0, we don't end up with an indeterminate form. And the way that we're going to do that is through factoring. So look at the numerator and look at these two terms. In these two terms, the elements that they both have in common is that they at least have one delta x in their term. And so by having at least one delta x, we can go ahead and factor that out, and we end up with the following expression. So you'll have the derivative of f of x is equal to the limit as delta x approaches 0. And by factoring out that delta x, we'll write 2x plus delta x divided by delta x. And so notice that with this format, you have a delta x in the numerator and a delta x in the denominator. And by having this, we can go ahead and cancel them out and write the following expression. The derivative of f of x is equal to the limit as delta x approaches 0 of 2x plus delta x. And so with the expression that we have right now, we can just go ahead and plug in 0 for delta x and evaluate the limit of this expression. And so we get that the derivative of f of x is equal to 2x plus 0. Taking that to the final step, we get that the derivative of f of x is just 2x. And that's your final answer. Now, as you go along in your calculus class, you'll find that there's a much easier way of computing the derivative of a function using the power rule, but it's important to know that you can also find the derivative of a function by using the definition of a derivative. Remember that this mathematics was developed centuries ago during Newton's time, and they didn't have the advantage of knowing the power rule. And so these derivatives had to be computed through the definition of a function's derivative. All right, so we'll go ahead and stop right here and go ahead and check out my part 2 differentiation video, and I'll go ahead and show the differentiation of the function f of x, which assumes a curve of the square root of x. All right, until then, see you later, guys.